going to do here, okay, yeah, there we go. What I'm going to do today is we're going to move to a new topic, which is the topic of disturbances in combusting flows. And so if you again think back to kind of the way all this discussion has been laid out, is the first lecture I talked about some of the general practical problems, what I call the operability issues associated with steady flowing combustion systems. I talked about blow off and flame stability and flashback and combustion instabilities. And then what I've tried to do with these other lectures is kind of do a deep dive on the fundamentals which influence those very important practical topics. And so each one of these we could spend many, many hours on, but the time is somewhat limited. So what we're going to do here is try to give you an overview of some of the issues around, try to help you understand some of the background of combustion instabilities and more fundamentally, disturbances in combusting flows, how disturbances are generated, how they propagate, and then also the sensitivity of flames to disturbances. What happens when you excite a flame with flow disturbances? How does the flame respond? So that's what we're gonna do today. Just as an introduction, let me just spend just a couple quick minutes motivating this topic. And as I mentioned, the topic of disturbances in reacting flows, particularly harmonically oscillating disturbances, is very, very much motivated by combustion instabilities. How many of you here are working on this problem for your own research? Yeah, so a good number of you. It turns out that for many combustion applications, particularly low NOx combustion applications, this is the single biggest problem and challenge associated with combustor development. And really what you have is that you have heat release. The flame is converting reactants into products and generating heat release, and that rate of heat release is never constant in time. It's fluctuating. You have turbulent fluctuations which are modulating the rate at which reactants are converted into products. However, when you take the flame and you place it inside of an acoustic resonator, like an organ pipe or a piece of pipe that has natural acoustic modes, what happens is that you have a mechanism for feedback. So in other words, the flame there's always disturbances. Those disturbances are causing the rate of heat release and the rate of conversion of reactants to products to oscillate, and those are also generating sound. And so flames are very, very much like speakers. If you think about the way that a woofer or a bass speaker, a low-frequency speaker, the way it makes sound is it's what we call a monopole source of sound. All right, and a monopole source of sound is simply a sound source that is just pushing air out of the way, and that makes sound. So if you take a woofer or a bass speaker and you just set it out in the open, it's going to be and you turn it on, you'll find that it's very inefficient at making sound. It's shaking, or the cone is shaking around back and forth, but it's making very little sound. But when you take that bass speaker and you put it inside of an enclosure, inside of a cabinet, what happens is when that cone moves out, it basically compresses the air a little bit, and that compression generates a propagating sound wave. When it's not in the enclosure, when the cone moves in one direction, the air that was in front of it just simply moves around to the backside, and there's no compression of the air. You're just sloshing the air around. You're imparting some kinetic energy into the flow, but in order to generate sound, you have to compress the air. You have to cause a little bit of compression. In the same way, flames make sound by creating volume. Just as a woofer, you can think of it as creating volume. It's pushing air out of the way. When gases go through a flame, they expand, right? So you go from reactants to products, and there's an expansion. So flames are sources of volume flow rate, right? Mass flow rate across a flame is conserved. Volume flow rate is not conserved. Flames increase volume flow rate. They're sources of volume flow rate. So if the rate at which the flame is converting reactants to products is changing in time, that means that volume flow rate source is changing in time. And so therefore flames make sound. Just as simple as that. So that's the bottom part of this loop. And then when you take a flame and you put it inside of an enclosure that has natural acoustic modes, you get the top part of this feedback loop, where those sound waves, they maybe propagate away from the flame, they reflect off of the end of your combustion chamber, they come back and they disturb the flame. And flames, as it turns out, are very sensitive to sound. In fact, we're going to spend the whole part of the second half of this class, the next hour and a half, talking about and quantifying flame sensitivity to sound. And what you end up getting here is a feedback loop, right? Just like if I walk too close to this speaker here, we're going to get a feedback loop where, see if we can make it happen. Not sure it'll happen, but okay, I won't make a screech in your ear. But you know, the same deal is that speaker is taking my voice, it amplifies it, but then if I'm at the right place in this room, the speaker's, this microphone is going to hear the sound made by that speaker, amplify it, and you can get very large oscillations. You get this screeching sound, right? Feedback. And the same thing is happening during a combustion instability. Actually, Professor Menon, who's going to be giving your talking starting tomorrow, he's a colleague of mine at Georgia Tech, and this is a nice video that he's made. This is a large eddy simulation. This is actually, this is not during a combustion instability, this is an ignition transient. But the same thing is happening when you're igniting the flame. There's this, all of a sudden, there's this burst of gas expansion. So you can see these waves, these are pressure isobars, and you can see these waves radiating away. The flow is going left to right. These are fuel nozzles. The flame is nominally here and here. And you see these sound waves radiating away. So when we have combustion instabilities, they occur at very specific frequencies. So if you take a flame and you just put it in turbulent flow and you don't have in it, but it's not in an enclosure, you lose the top part of this feedback loop, and you just get turbulent combustion noise. So turbulent flames make sound. They make noise, and it's a broadband sound. But when you take that flame and you put it inside of a resonator, what happens is it acts as a very narrow band filter, and those oscillations become occur at very specific frequencies, and those frequencies are associated with natural acoustic modes of the combustion chamber. So, you know, and this is an experiment you can try at home. You know, if you have this is an example of a Helmholtz resonator, right? You take a Helmholtz resonator, any enclosure where you take a volume and then you constrict it to a neck, so it could be a milk jug or a bottle like this, and you blow over the top of it. How many of you have done this before? Know what I'm talking about? And you hear a whistle, right? And that whistle is the natural frequency of that Helmholtz resonator. So this right here is a this is what happens when you put a bunch of nerds at a conference who sell instrumentation, and they have nothing to do in the evening, is they apply their instrumentation to what they're doing in the evening. So this is from a company, Alta Solutions, which sells acoustic instrumentation, and apparently they were bored. And so what they did was they did this experiment on a beer bottle, and this is what they measured. And you see there's this 190, and the main thing I want you to see is look how narrow band. This is not broadband distributed turbulent stuff. You get this is the spectrum, so frequency in hertz and amplitude. And the frequencies aren't even that important for what we're trying to talk about, but just notice how the energy is concentrated in very narrow spectral peaks. Some of these spectral peaks are associated with what's called the Helmholtz mode. Some of these are modes bouncing up and down. Some of these are going side to side, and these are what flames are exciting. Now, as I mentioned, and we're going to dig into this in a lot more detail, but I've talked about the bottom part of this feedback loop, why flames are making sound. The top part of this loop is flames being sensitive to sound. This is a really nice video from École Centrale, from Professor Candel. And what you're looking at here is a Bunsen flame, just a very simple Bunsen flame. Flow is going bottom to top. And what they did was they put a speaker on the bottom of the tube, and so the flow rate coming out of this thing is pulsing. So this is not a self-excited system. This is a forced system. They're imposing the forcing on it. And this is a Schlieren image. So what you're looking at is the flame. So there's a big density jump across the flame right here. And then this right here is the hot combustion products, the interface of the hot combustion products with the ambient gases. And so there's a couple things you can see from this. First of all, you'll see that this flame, if there was no forcing, it would just be a simple V shape. It would be a simple Bunsen flame. But because of the presence of the forcing, you generate these wrinkles on the flame. You see these wrinkles convecting downstream. And then what I also like about this video is this image is it's not only the flame, but also by looking at the gas plume, you can get an idea of the volume of the reacted gases. And you'll see that not only is the flame moving around, but you'll see that this gas plume is moving side to side. And what that's telling you is that this volume flux of coming out of the flame is getting modulated in time, right? If the volume flow rate coming out of the flame was constant, you wouldn't see this flapping like you do. But clearly, the rate at which volume is flowing out of the flame is getting modulated in time, and so therefore this gas plume is oscillating. How many of you have seen a Rubens tube video? I showed it a year ago. It's so much fun, and I always like to show it right after lunch because it wakes you all up. So let me just show it. This is but there's a serious part to this as well, but it's also a good way to wake everybody up. Is I've talked about how flames are sensitive to sound, but it also turns out that not only is the flame sensitive to sound, but the whole combustion system is sensitive to sound. All right, combustors, unless you are working in a scramjet where the flow is supersonic, those sound waves generated by the flame, they go everywhere, right? They go downstream, they go upstream. If your fuel system is not choked, they propagate into the fuel lines. And so the airflow rate coming into the combustion system will oscillate. The fuel flow rate coming into the combustion system will oscillate. The mixing of fuel and air oscillates. If it's a spray, if it's a spray combustion system, the spray cone angle will oscillate. The atomization will oscillate. The whole thing is sensitive to these perturbations. And this is a nice little video that demonstrates this point. You can get it off of YouTube, and I'll just play it for you here.
Bring it down, but it involves open flames, and some people have issues with open flames. So let's do a classic physics experiment called the Rubens tube.
Can you hear that in the back?
I really want to break it down, but it involves open flames, and some people have issues with open flames. So what we have here is a lane of PVC pipe, has about 100 or so holes drilled in half-inch increments. It has a foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some
Could you hear the beginning in the back or not? Pardon? Okay, we got time. We'll go back. It's worth it.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So what we have here is a lane of PVC pipe, has about 100 or so holes drilled at half-inch increments. It has a foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. All right, as you can see, we have some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency. As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is you're having the sound compressing here and not compressing here. The low pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency, we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now, let's throw some music at this. How about some Dave Brubeck?
never figured out why the flame doesn't like it right over here.
All right, now that's good. I'm going to turn off the gas, have the fun. That's a Rubens tube.
All right. Hope you all woke up. But as I mentioned, the point I was trying to make from that video was that the whole system is sensitive to sound, right? In that case, it was the whole fuel delivery system you can see is getting modulated by the sound waves. Okay, well, with that as just a quick primer, now let's move into the next topic. Just make sure my battery's getting charged here. Okay. And what I want to talk about are fundamental disturbance modes. So ultimately, you can see combustion instabilities are associated with disturbances. I've used the word acoustic a lot, and so part of those disturbances are acoustic, but they also involve interactions with vortical disturbances, and they oftentimes these acoustic waves are exciting hydrodynamic instabilities of the flow. So you have shear layers. These flows have shear layers. They're unstable already without acoustic excitation. But now you have these acoustic modes bouncing around. They're exciting these shear layers. You have the potential for, the flame is generating entropy, but you have the potential for the temperature after the flame to be getting modulated, which are what we call entropy disturbances. And so in general, if you were to do a detailed simulation or get a comprehensive data set from an unstable combustor, and you made measurements at a given point, you would measure fluctuations in velocity, in pressure, in temperature, in density, in vorticity. So all these disturbances are going on. And what I want to talk about now is how we can decompose an arbitrary disturbance field into three fundamental types of disturbances. So in other words, what I'm going to be arguing here is that we have these observables that we're all very familiar with, basically fluid mechanic parameters and thermodynamic parameters, like pressure, like temperature or density, like velocity. But what I'm going to suggest is that these are the things you measure, that you observe, or that you have a physical intuition for. But more fundamentally, there's these three kinds of canonical disturbances which manifest themselves in those observables. All right, and it turns out that that many fairly complicated phenomenon, for example, the velocity. When you make measurements of the velocity field in an unstable system, you'll find that you have some fairly complicated patterns. But if you recognize that the velocity is sort of your observable, but what's influencing the velocity are these three, you're actually observing the superposition of three fundamental canonical disturbances, it actually makes the problem a lot simpler. So that's what we're going to get into here. And we're not going to have time to talk about some of these other more advanced topics. We're just going to try to focus our attention here on these disturbance modes. And so really what we're talking about here is looking at, well, we're going to look at how small amplitude disturbances propagate. And we're going to start, just to kind of set the stage, I'm going to think about a very, very simple flow. I'm going to assume I have a spatially uniform Inviscid flow. All right? So if I have a flow where there's no gradients in density or temperature, and I take a look at, if I have a spatially homogeneous background flow, and I add a very small disturbance into that flow at time t equals 0, what happens next? What happens to that disturbance? That's what I want to look at. All right? And you might say, wow, that's a really boring problem. Who cares about spatially homogeneous flows that are Inviscid? But we're going to start simple, and then I'll show you how we can add layers to understand more complicated things. So what we're going to do here is we're going to basically linearize the Navier-Stokes equation. So you take the Navier-Stokes, actually the Euler equations, because we said we're going to assume Inviscid. So we're going to take the Euler equations, we're going to linearize them. So we're going to, in other words, we're going to assume that I can take every variable, let's just say the pressure. It's a function of space and time, x and t. What I'm going to do is I'm going to write the pressure as a part that's not oscillating. I'm going to call this the mean, P naught. And a fluctuation, P1. Now, because of my assumption that I'm assuming a spatially homogeneous background flow, this nominal value of pressure is not a function of space or time. It's just a constant. All right? And then I have a small disturbance. So by assuming an infinitesimal disturbance, what I'm assuming is that P1 is orders of magnitude smaller than P naught, which, by the way, is a pretty good approximation for pressure. You know, as I'm talking to you now, the fluctuations in pressure, you know, are orders and, you know, 6 orders of magnitude less than the mean pressure or something like that. So oftentimes for acoustic problems, what we're going to linearize, and it's a very, very valid approximation. But the disturbance is a function of space and time, and I want to look at what is the space-time dependence? How does this thing act? And as another example, density. So density has some nominal value and then a disturbance. Velocity, nominal value and a disturbance. So what you can do now is with these approximations, with this decomposition, you can go to the Navier-Stokes equations and you can linearize them. All right? How many of you are familiar with the linearization process? Okay. Well, let's just do a quick example just to illustrate this. So if we just take the continuity equation. As an example. All right. What I want to do now is I want to expand it. I'm going to write this as that, right? And now, okay, well, rho naught's not a function of time. And then, remember, rho naught and u naught are not functions of space, so this divergence vector, those things, and it turns out that once you, what you're going to end up with here is, so I can, in other words, I can pull the rho naught or the u naught out. So I'm just going to skip a step or two. Did I make a mistake? Okay. Okay, if I and it was something like that. And then so what I have here is, and then what the essence of the linearization approximation is you say, okay, this term is a product of two really, really small quantities, whereas this one has, so this term is going to be of order, you know, if this term, if I introduce a small parameter, say epsilon, and this term is of order epsilon smaller than that one, then this term will be of order epsilon, order epsilon, order epsilon, order epsilon squared. And then I basically, this is higher order, so I'm going to neglect that. And so this would be an example of the continuity equation, an equation which describes the space-time dynamics of a small amplitude disturbance in density and how it's related to a small amplitude disturbance in velocity. All right? And it's linear. It's a linear equation. In the same way, I can do the same thing for the energy equation. I can do the same thing for the momentum equation. And I'll end up with a set of linearized equations. Well, I'm going to skip a whole bunch of steps now and just kind of jump right to the answer. All right? But you take the linearized Navier-Stokes equations, and it turns out that you can then cast them as these three equations. And so you can write an equation for the vorticity that looks like this. All right, and I'm kind of, like I said, I'm kind of jumping ahead to the answer a little bit because you might ask, well, why am I looking at vorticity? We haven't talked about vorticity before. But I'll explain why in a little bit. But if the vorticity, oops, let's. So omega 1, capital omega 1, is just the curl of U1. It's the, remember, the subscript 1 is the fluctuation. And so what this equation says is you have the substantial derivative So the total derivative, capital D, when I put the subscript naught, what I'm implying there is that the convection term is just convection by the mean flow. All right. In general, the convection term would also have a part due to the fluctuation, but it turns out that that's a nonlinear part. Okay. So what I'm looking at here is so what this says is that I can write an equation with these approximations. So if you take the curl of the momentum equation, remember in general the vorticity equation comes from taking the curl of the momentum equation. If you take the curl of the linearized momentum equation, you end up with a very simple equation for the vorticity. Normally the vorticity equation is all these source terms, baroclinic terms, and stretching and bending terms, and dilatation terms, and things like that. They all go away, and you end up with just this expression. So that's one equation that falls out. If you take the energy equation and you write it in terms of entropy, all right, remember you can write the energy equation in terms of entropy. You can similarly write this very simple equation for the entropy. Script S denotes the entropy. So this is the fluctuating entropy. All right. And then finally, if you take the energy equation, the momentum equation, and you solve them simultaneously to eliminate the velocity, you can write this single equation for the pressure. All right. So momentum, and so bottom line, you take the linearized Navier-Stokes equations and you add the linearized energy equation, and you can recast them as these three equations. And there's a reason that I'm recasting them in these three equations, because what I'm going to show you is these three canonical disturbance modes are vorticity disturbances, entropy disturbances, and acoustic disturbances, which is why I'm writing them this way. Okay? So, in other words, there are three fundamental types of disturbances. Disturbances in vorticity, disturbances in entropy, and acoustic disturbances. And acoustic disturbances are volume fluctuations, or dilatational disturbances. So, remember, a vortical disturbance is incompressible, but it's rotational. Whereas the acoustic disturbances are compressible, but irrotational. So you may have seen this that you can do this general decomposition of a velocity field. And so what we're doing is we're decomposing it into a part that's incompressible but rotational, plus a part that's compressible and irrotational. And then we also have to add an entropy part to it. So if we look at these equations, what is this? I mean, physically, this equation is saying is that it says the substantial derivative of the vorticity fluctuation is 0, right? So what that means is, remember, the substantial derivative, that just says if I'm going with the flow, if I'm taking a Lagrangian point of view, if I'm moving with the flow and I'm tracking something. In this case, if I take a bunch of molecules and I paint them green, all right, and so I'm tracking them, and I watch those molecules in time. And in this case, what I'm asking is, is what is the time rate of change of vorticity of that control mass? And what does it say? What is the time rate of change of vorticity of that control mass? 0, right? So what it's saying is that for a fixed volume of fluid, you know, I have some vorticity, it's moving with the flow. It's saying that the vorticity is constant for a control mass with these assumptions. Okay? Now, if I have let's suppose that I have a vorticity measurement device and it's sitting at a fixed position and disturbances are going by me. Does that say that the vorticity is 0? No. It's saying that there's no change in vorticity. So stuff can be convecting by me, and I can have blobs of big vorticity, you know, regions with high vorticity and low vorticity and high. And as they'll convect by me, as I'm measuring vorticity, I could see time change. I could see variations. I could see this term being non-zero, is basically what I was asking, because it's going to equal negative U naught dot grad omega 1, right? So if there's a spatial gradient in the vorticity as it's getting convected by me, I'll see a fluctuation. But what this says is that these vortical disturbances are moving with the flow. It says the same thing about the entropy. So again, if I'm following a fixed mass of fluid, and I'm measuring its entropy, the entropy is constant of that fixed mass of fluid. At a fixed point, if I make an Eulerian measurement, the entropy could be fluctuating in time. And then finally, what this is, does anyone recognize this equation? Yep, it's a wave equation, and it's specifically a convective wave equation, but we don't need to worry about that. So this is a wave equation. It describes a disturbance, in this case the pressure, that's moving with the speed of sound. All right? So what this is telling you then is that vortical and entropy disturbances are moving with the flow with constant amplitude, and pressure disturbances are moving at the speed of sound. All right? Okay, well let's, so this is a summary of those disturbance equations. What I want to do now is I want to further decompose perturbations by their origin. So in other words, what I'm going to say is, let me go to a new slide. What I'm going to kind of motivated by those equations, what I'm going to argue is that there's these 3 canonical disturbances, and then they manifest themselves in all your other disturbances. So in other words, I'm going to say I have acoustic, vortical, and entropy disturbances. So in other words, if I'm looking at the density, this is my macro observable. This is what, you know, if I'm measuring it, it will have an acoustic component plus a vortical component plus a component due to the entropy. And I'm going to use this delta symbol to denote the acoustic part, the omega to denote the vortical part. So in other words, what I'm saying is that the acoustic fluctuation induces some fluctuation in density. The vortical fluctuation induces a fluctuation in density. The entropy fluctuation induces a fluctuation in density. And what I'm measuring, or what I'm computing when I'm calculating density, is the sum of those 3. Okay? Similarly, the velocity. You know, it's going to equal U1 delta plus U1 omega plus U1 entropy. And I can just go right down the list for every single variable. Here I gave, you know, we can do the same thing for pressure, do the same thing for temperature. We can even do the same thing for vorticity and entropy. Okay? So in other words, you know, like this P1 omega, that's the pressure fluctuation induced by the vorticity mode. Okay? Now, and then what I'm going to do is I'm going to take these decompositions for every one of my variables, and I'm going to plug them back into the linearized Navier-Stokes equations. Because they're linearized, I can decompose them into subsystems, right? There's no nonlinear cross-coupling between them. And so I can write a system of equations just for the acoustic part, and an acoustic system of equations just for the entropy part, a system of equations just for the vortical part. All right? And I'm sketching out the solution process for you. I'm obviously, for the sake of time, I'm skipping over a lot of stuff. But if you do that, so we take the linearized Navier-Stokes equations, We substitute these things in and we write these subsystems of equations. If we do that, what we'll do with the next 3 slides is we'll look at what happens with the vortical subsystem, the acoustic subsystem, and the entropy subsystem. So we'll start with the vortical subsystem. And so this, just to read this, so omega 1 omega, this is the vorticity fluctuation induced by the vortical mode. What that says is that's equal to 0. The substantial derivative of that is equal to 0. So that's no surprise. It just says that I have this vortical disturbance due to the vortical mode, and it's just moving with the flow with constant amplitude. This part is kind of interesting. Somebody interpret, what does this say? If P1 omega is equal to 0, what does that mean? The vortical mode induces 0 fluctuation in pressure, right? So, in other words, if I'm measuring the pressure, I have a pressure probe right here. Vortical disturbances are convecting by me. I won't see them, right? The first order, right? The pressure fluctuation induced by that vortical disturbance is 0. In the same way, this says the entropy fluctuation induced, the vortical disturbance induces no disturbance in entropy. It induces no disturbance in temperature. It induces no disturbance in density. Okay, so let me ask a quick question for you. How many of you are familiar with jet noise and Lighthill's theory of jet noise? Nobody. Okay, no problem. Let me pose it a different way then. It's a well-observed fact that vortical disturbances make sound. All right, jet noise is a great example of that. Jets are turbulent fluctuations in jets. What the fundamental mechanism is, you have fluctuations in vorticity. It's making lots of sound. When you hear a subsonic jet flying by and you hear that noise, you're hearing vortical fluctuations. So how does that observation jive with what I wrote here, where I said P1 omega is equal to 0? It's a nonlinear term. That's right, exactly. Yep. So key part is, and the reason I want to emphasize that is you don't forget the 2 key assumptions of this analysis: homogeneous flow, linear. Right. So vortical fluctuations do induce pressure fluctuations, but they're higher order. They're quadratic terms. Okay. So the first order. So what that means is that a vortical disturbance of order epsilon induces a pressure disturbance of order epsilon squared. All right? Same with entropy, same with temperature, same with density. Okay, so let's just read this. So what it says here is vorticity and the velocity induced by the vortical disturbances, they're convected by the mean flow, but they induce no fluctuations in any thermodynamic variable: pressure, density, temperature, or entropy. Okay, so that's the vortical mode. This is how the vortical mode shows up. All right? So if we go back over here, we say, how is this vortical disturbance manifesting itself? Well, it's not manifesting itself at all here. It's manifesting itself in the velocity. It's not manifesting itself at all in the pressure. It's not manifesting itself at all in the temperature. Okay, let's look at the acoustic mode now. All right, so what this is saying here is remember now the subscript lambda is the acoustic mode. It says that the pressure fluctuation induced by the acoustic mode satisfies a wave equation. So again, probably no surprise because of the equation I showed you earlier. This is a wave equation that describes sound wave propagation at the speed of sound. This right here says the acoustic mode, which remember is essentially a compressible but irrotational disturbance. Here it says it's irrotational, right? you're seeing that the vortical disturbance induced by the acoustic mode is 0. Similarly, this says that this acoustic mode, that the entropy disturbance induced by the acoustic mode is 0. Right? So in other words, this acoustic disturbance propagates isentropically and irrotationally. That's what this is saying. Okay, now these terms, so not everything is boring. These terms are non-zero. So what this says is that the density, the pressure, and the temperature associated with an acoustic disturbance are all oscillating. And what it also says is, as it shows here, is the density, temperature, and pressure, they're locally and algebraically related. And in fact, these are the, if you were to calculate the isentropic relation between pressure and temperature, and you were to linearize it, so if you remember, the isentropic pressure-density relation is P equals some constant times rho to the gamma. If you were to assume that the pressure and the density disturbances are small and linearize that expression, you would get that. That's what this is coming from. And so it says, so when I say they're locally and algebraically related, what that means is that the local pressure fluctuation is related locally, is related to the local pressure, I'm confusing myself, the local pressure fluctuation and the local density disturbance at every instant in time at a given point in space are related by this expression. They're not related through, as opposed to, for example, the velocity and the pressure. They're related through derivatives. The time derivative of the velocity is equal to the spatial gradient of the pressure. So the pressure and the velocity are not locally and algebraically related. Rather, the acceleration is proportional to the pressure gradient, is what this says. But this says that the pressure and the density and the pressure and the temperature are related, are all locally and algebraically related. So what that also means is that if they're oscillating in phase with each other. And then, as I just mentioned, the velocity and the pressure, it's the acceleration which is related to the pressure gradient. This is, you'll recognize this. This is just the momentum equation. F equals ma. Force, pressure gradient, is mass times acceleration. Okay, that's the acoustic mode. And then finally, we have the entropy mode. All right, so what this says is that the entropy disturbance associated with the entropy mode, well, this is just the convective term, it's equal to 0. These right here say that the entropy mode induces no fluctuations in pressure, no fluctuations in vorticity, and no fluctuations in velocity. So these entropy disturbances are not flow field disturbances, in other words, because there's no velocity effect. Whereas you can see that these terms that not everything is 0. So in other words, an entropy disturbance, it is manifested in a density disturbance and a temperature disturbance. Okay, so that's what that says. So the entropy mode manifests itself as disturbances in thermodynamic quantities, but not in flow field quantities. So this next table here summarizes all this. And does anyone follow these notes online? This table's not in your notes because I added it this morning. If you were looking for it. But this summarizes this. So these are your observables that I just talked about. These are the things that actually show up in the energy equation or momentum equation. These are these experimentally or computational, well, they might be accessible computationally, but generally these are these more fundamental disturbances, but they're not experimentally accessible. And this shows how they're manifesting themselves. So in other words, what it says is that if I'm looking at the pressure, I'm actually directly looking at the acoustic mode because the entropy and the vorticity don't cause any influence on the pressure field, which is why we oftentimes synonymously equate the pressure fluctuations in the acoustic mode, is because the entropy and the vorticity disturbances are 0. If I'm looking at the velocity, so if I'm measuring velocity, what I'm measuring really is the superposition of an acoustic disturbance, which is moving at the speed of sound, and a vortical disturbance, which is convecting with the flow. If I'm looking at the density and the temperature, I'm looking at the superposition of an acoustic disturbance and an entropy disturbance. Okay, so that summarizes that. Well, let's just make a a couple of comments on this decomposition. So first of all, in a homogeneous uniform flow, these three disturbance modes, they propagate independently. All right? So they're doing their own thing. What you're measuring is the superposition of those three disturbances, but they're not interacting in any way at all within these approximations. And so in other words, they are totally decoupled. So these fluctuations, they're completely independent of each other. So I talked about how the velocity is a superposition of a vortical disturbance, of an irrotational compressible disturbance and an incompressible rotational disturbance. But those two disturbances are completely independent. I'm measuring their superposition. I may not be able to actually directly access them individually, but they're not interacting with each other. And also, all those terms, all those disturbance equations were sourceless. The right-hand side of those equations was all zero. You know, d omega naught by dt was zero, or the wave equation had, and so what that means is there's no sources or sinks of any of these disturbances. Once they're created, they propagate with constant amplitude.
Question?
Yes?
The vortical disturbance is not influencing temperature because it is inviscid, considering the viscous distribution?
It's also because it's incompressible at this order. At first order, the vortical disturbance causes no change in density or pressure, or therefore temperature. If I included vorticity, what you're asking is if I linearized it and added a viscous term, would the vorticity induce a temperature fluctuation? And I think the answer is still no. I have to think about that one, but I'm pretty certain the answer would still be no within the linear approximation. Okay, well let's talk a little bit more about this. So first of all, acoustic disturbances propagate at the speed of sound. Vortical disturbances propagate at the bulk flow velocity. Well, that's a big difference, right? And so what that means is, well, there's a couple different implications about that, but one of those is that there's two completely different length scales to the problem. And in order to illustrate that, let's just suppose I have a magic disturbance generator, okay? Here's my magic disturbance generator, and I'm generating either an acoustic disturbance or a vortical disturbance with a period of t, capital T. This t is not temperature now, but it's the period, which is 1 over the fundamental frequency, all right? So I just go ping, 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 and I'm generating a disturbance. Well, if my disturbance generator is acoustic, I will generate a train of disturbances. I'll just give them vertical slashes. So this is the disturbance that I generated 5 pings ago, 4, 3, 2, and this is the one that I'm generating right now. Well, what's the different distance between these pings? Yeah, the wavelength, right? Which is equal to the speed of sound times the period, right? These disturbances are moving at a speed of c, and it's had an amount of time, capital T, to go, and so c naught times t is equal to c naught over f. So acoustic properties are varying over an acoustic length scale, all right? And I'm going to lambda, I'll denote that as the wavelength. It's c naught over f. Now, if my magic disturbance generator was generating vortical disturbances, these are getting propagated by the flow. And so what I would see would be this train of disturbances. The distance between those, they're not moving at a speed of sound. They're moving at the mean flow velocity, u naught times t. So my wavelength, what I'll call a convective length wavelength, lambda c is u naught over f. Okay? So in a low Mach number flow, u naught is going to be much smaller than c. That means that this vortical wavelength is going to be much smaller. Excuse me, this convective wavelength is going to be a whole lot smaller than the acoustic wavelength. In fact, the ratio of these two wavelengths is the Mach number. So if the Mach number is 0.1, that means I have a problem with two very, very different length scales in it. The acoustic component, long length scale, the entropy and the vortical component, short length scale, right? So if we go back here to this chart, let's assume everything's harmonically oscillating with one frequency. So I only have one time scale in the problem, all right? One time scale, but I don't have just one length scale. I have two length scales, all right? So, for example, the pressure is going to have the pressure disturbances will also have a single time scale and a single length scale. Whereas the velocity disturbances, being a superposition of these two kinds of disturbances, one time scale, but two discrete length scales in the problem. Okay? And then, or more generally, if you had a problem where you had multiple frequencies, for every time scale, you would have two length scales associated with that time scale. Yeah?
You said the ratio of the length scales is the Mach number.
Yeah.
So does that mean that sonic conditions, these length scales approach each other?
They're the same, yes.
So will there be interactions between the Vorticity mode and the acoustic mode?
Not unless we relax some of the approximation of either homogeneous flow or linear. The interactions happen, well, we're going to talk about this later. There's three mechanisms for interactions, but none of them, but it doesn't have to do with the Mach number.
Convective velocities are less compared to the mean flow velocities.
So this, when we say the convective velocity, it is the mean flow velocity for this problem. Since there's no spatial gradients, everything's moving at the mean flow, at one value. There's only one velocity scale, U0.
So do the scales also approach each other at non-sonic conditions, like a subsonic condition? If in the low Mach number limit, do the length scales and time scales approach each other? What are the conditions for them to approach each other?
So they won't. That's the key point here is that those length scales in a low Mach number flow are going to have a order Mach number variation between them. So this actually turns out to have lots of important implications for problems in different fields, but I'll give you one example. Let's suppose that I'm trying to understand, I'm going to draw a flame. Flow is going left to right. I want to understand how this flame is behaving during a combustion instability. And so, and during this combustion instability, there's acoustic waves bouncing around, all right? And those acoustic waves are exciting vortical disturbances, all right? So I'll have both acoustic velocity disturbances and vortical velocity disturbances coexisting. But because of this disparity in length scale, it's very, very common, at least for axial instabilities going back and forth, for the acoustic wavelength to be really long with respect to the flame length. So in other words, if this is L, I'm going to call this LF. LF is my flame length. I just spit on the screen. Sorry about that. I can take this ratio, and it's oftentimes much less than 1. It doesn't have to be, but I'll just say that oftentimes it is. All right? And this is what we would call an acoustically compact flame. A flame where the size of the flame is really small with respect to a wavelength. It turns out this is a really important limit because in this limit, the spatial distribution of the heat release doesn't matter. It's just whatever the instantaneous spatially integrated heat release. However, in many cases, even when you have an acoustically compact flame, it may not be convectively compact. So that, another way of saying that is that even though the acoustic wavelength is really long, the convective wavelength, which as we just said is going to be shorter by order Mach number, you can see that in fact LF on lambda c is bigger than 1. For this example I just drew, it looks like it's close to 2. So for the way that would manifest itself is, for example, if you had these shear layer disturbances. There's multiple shear layer disturbances that fit within the flame length. And so modeling the influence of the flame on the acoustic field is oftentimes a much simpler problem because of this compactness compactness limit than modeling the influence of these convecting vortical disturbances on the flame, because you can't apply the same limit. So I just noted, if you didn't completely follow that, that's fine. I just wanted to note that in passing. Okay, so let's just talk a little bit more. So if we talk about the acoustic disturbances are, I say that they're being true waves. When I say true waves, let me explain what I mean by that for a minute. What is a wave? A wave is something which carries information and energy without carrying mass, right? So in other words, let's suppose that I want to propagate some information or some energy to the back of the room. Well, one way to do that is for me to just walk back there, and there it is, right? Another way is, and that's really what convection is, all right? Another way is sound waves, which is a compressional disturbance, right? So as I'm talking, I'm compressing the air in front of my mouth, which then compresses the air in front of it. And it's like if I was to take a whole row of billiard balls and just hit one. Well, the ball that I hit here doesn't go all the way to the back of the room, but yet I'm inducing motion of a ball all the way at the end if I have a continuous series of balls. So that's really what I would call what a true wave is. And I'm putting the word true in quotes there. But the main thing is acoustic disturbances, they propagate information and energy without requiring convection. There's also, they reflect off of boundaries, right? So acoustic waves reflect. These vortical disturbances and entropy disturbances, they don't reflect. They just convect. So what that means is that, when I'm talking, sound is bouncing off of the floor, sound is bouncing off of walls, things like that. And this property, the fact that sound waves reflect, this is what gives you natural acoustic modes of closed combustion devices, right? This is why an organ pipe has natural acoustic modes, or any kind of resonant musical instrument has natural acoustic modes. It has to do with this reflection of sound waves off of boundaries. Now, in contrast, let me just see, I don't have any data there. Vortical disturbances and entropy disturbances, they are carried by the flow, all right? And so, if I were to compare and contrast, let's just say we're looking at the velocity field, all right? Let's go back to this table here. We said that the velocity field is a superposition of acoustic disturbances and vortical disturbances. Well, the acoustic disturbances, as we just said, they're moving with the speed of sound. They have one length scale. The vortical disturbances, they're moving with the flow velocity. They have another length scale. But there's also another property about them. The acoustic disturbances in a low Mach number flow, the structure of the acoustic field is relatively insensitive to the details of the velocity field. So you could have 10 different combustors with 10 completely different flow fields. As long as the Mach number is low, you could have essentially virtually the identical acoustic field. Same natural frequency, same modal structure of nodes and antinodes of the pressure and velocity field. If you were to make a measurement, take a microphone and map out the pressure field, 10 combustors, 10 totally different flow fields, essentially identical pressure fields. All right, and that is because in a low Mach number flow, the mean velocity has a relatively small influence on the acoustic disturbances. That certainly particles are moved by the flow. There's bulk convection, but the convection associated with just the molecular collisions is happening so much faster that it's dominated by that. What controls acoustic fields is the distribution of the sound speed, right? The speed of sound is what has a dominant influence on the acoustic field, as well as your boundary conditions, which controls how sound waves reflect off of things. Okay, so just to summarize that, the acoustic field is controlled by boundary conditions and the distribution of the speed of sound, almost independent of the velocity field in a low Mach number flow. All right, so that's one piece of the velocity field. which is only cares about what's the sound speed field, what are the boundary conditions. The other piece of the sound field, the other piece of the velocity field is the vortical disturbance field, and this is profoundly sensitive to the details of the velocity field. And that is because how do vortical disturbances move? They're moved by the velocity. If you got 10 different mean velocity fields, you're going to have 10. You could have 10 completely different patterns of vortex convection. And so, two completely different sensitivities to the details of your flow field. So let me just show you an example now of data. This is data from Jackie O'Connor, who's a professor at Penn State, which just shows you how, by understanding these canonical modes, how you can really get a much better understanding of in this case, measured PIV velocity fields. So what we have here is a combustion field, a combustor. This is an annular reactant passage. Flow is going left to right. And you have a flame out here. There are acoustic waves bouncing up and down this way. There's a transverse acoustic field. This is an instantaneous velocity field. All right. So if you look at this instantaneous velocity field, you can kind of see these vortical patterns here and here and here. If you go down here, it looks like the vortical disturbances, these vortices have maybe dissipated. And you can the velocity vectors are almost up and down, which is associated with this transverse wave field. But let me just jump ahead two slides real quick. When we measure the magnitude of the velocity fluctuations, forget the fit for a minute, but the magnitude is the symbols. I'm plotting the magnitude of the velocity as a function of axial distance. All right. And there I'm plotting the phase of the velocity fluctuation. So what I'm doing here is, let me go back, and am I allowed to draw on this board? Just joking. I won't draw on the board, although it'd be nice if I could project on it. Let's see. Let's. Oh, okay. It's not a huge deal otherwise. Yeah, don't worry about it. Don't look. I'm serious. It's not. It's no big deal. It's all. I can draw it quick, real quick. Yeah, let me back it up one. Okay. All right, thanks. So in other words, if you were to take a measurement plane along here, what we're plotting is the magnitude of the velocity fluctuations and showing that they go like, whatever they look like there. They have this funny spatial modulation. Okay, so what I'm plotting here is the magnitude of the velocity fluctuation. So what that means is, at this point, if I go over here and make a plot of the velocity fluctuation as a function of time, let's suppose it looks like this. This is time. So let's just be careful about space and time here. So this is x here. So u prime, the instantaneous velocity fluctuation, might look like that at this location here. At this location here, there's a phase shift, but there's also a significantly smaller amplitude. Okay? So in other words, when I'm just to make sure this is not this plot here, this is not the instantaneous velocity, it's the magnitude of the velocity. So this is a harmonically forced system. The velocity is oscillating up and down harmonically with an amplitude given by this curve. And so what this is showing you is that, wow, the velocity is oscillating a whole lot more here than it is there, but then it's also oscillating more here. So what's going on? So in other words, if I were to then plot this point on this graph, again, there'd be a phase shift, but it would have a similar amplitude as the other one, so it might look something like this. Okay, so the way we can understand that then is if we go back to our table, we say, okay, the velocity field, what am I really looking at? When I'm measuring the velocity field, I'm looking at the superposition of an acoustic and a vortical disturbance. So let me just think about that for a minute, what that should look. So let's just back up and do a quick model problem. All right. Let's write the velocity field as a superposition of an acoustic and a vortical disturbance and say, what would the space-time dependence be if I added up a disturbance which is moving at the speed of sound and a disturbance that's moving with the mean flow velocity? All right. So what I have here, these are two traveling waves. These are disturbances which are traveling. So in a reference frame moving with the speed of sound, it's not changing, but you have here, this basically describes a disturbance with amplitude A sub lambda moving in the direction of positive x. As time advances, it's oscillating with a frequency of omega. All right. This describes a disturbance with amplitude A omega. This is a vortical disturbance that's moving with the velocity. All right. So what would happen if I have two disturbances oscillating at the same frequency, so one time scale, but they have two length scales, because one's C naught, the other's U naught, but I'm measuring their superposition. Okay? So just for simplicity, let's assume that these amplitudes are the same, all right? And you can use some trigonometric identities, and you end up with this. All right? And so what we have here is a term that's only a function of space, and here we have a disturbance, and here we have a term that's oscillating as omega t, and then it has a space-dependent phase. All right, so in other words, can I go back to that other software? Just dump out of it. So what I have there, another way of writing it is to say that u1 of x and t is equal to sum a of x times cosine omega t plus a phase, which is a function of x. That's what I have. All right? So I started out with a disturbance where the amplitude's not a function of x. Amplitude's not a function of x. When I add them, I get a disturbance whose amplitude is a function of x and whose phase is a function of x. All right? And so what I'm getting here is a harmonically oscillating disturbance with a spatially modulated amplitude. So if you actually, if you were to take a simple model like this now and relax the assumption, I just wrote this assuming that these amplitudes were the same. But if you use that same model and you just fit the real data, so this is the data, and if you fit it such that the acoustic amplitude is 0.6 times the vortical amplitude, you get this curve right here, and you get the solid line for the phase. And you can see it nails the measurement for the phase. The measurement for the amplitude, you can see some similarities. There's obviously the real disturbance field is a lot more complicated than simply a single, constant amplitude, constant phase speed disturbance, but it clearly captures the essence of the measurement. All right? So what you're seeing here in this case is when you take two disturbances with the same frequency, but they're moving at a different phase speed, what you're basically setting up is an interference field. All right? And so you have these two disturbances, one is moving fast, the other is moving slow. At some points, they're exactly in phase with each other. You get big amplitudes of oscillation. At other points, they're 180 degrees out of phase with each other, and they almost cancel each other. Now, if you plot the individual vortical component amplitude as a function of x, it looks like that. The individual acoustic contribution only looks like that, right? That's what I'm trying to show here. But if you take a disturbance with this amplitude dependence that moves at one speed, that amplitude disturbance that moves at another speed, and you end up with that. So for some of you may be familiar with standing waves in acoustics, where you get nodes, these node and antinode patterns. That occurs when you have two disturbances moving in opposite directions at the same speed. That's when you get acoustic standing waves. What this is showing you is you can get a similar modulation. This is not a standing wave, but you can get a modulation in amplitude, which looks like a standing wave, if you have two disturbances moving in the same direction, but at different speeds. That's what's happening here. Okay, so I guess this was a case study. The main reason I wanted to show you this case study was it shows how we can take complicated data from a real system, and if you were just to look at the data, you'd be scratching your head to say what's going on, but by understanding that there are these fundamental canonical disturbances, and what you are measuring is their superposition, it gives you some insight into what's happening. By the way, just give me 1 second. It would be wonderful if we could actually do these decompositions on data, if you could actually decompose the velocity into the acoustic and the vortical vortical component. It's really hard, right? The vortical part is going to be related to the first of all, you're going to be differentiating data, and then it's a complicated operation. Some people have done it on numerical data where they take, they'll take a DNS or an LES, and then they will decompose the disturbances into their acoustic and vortical and entropy part. And it's very illustrative. Yes? Oh, okay. All right, so last thing I want to do is let's go back to the beginning, all right, when we started this discussion. And I said I'm going to make some pretty severe assumptions. I'm going to assume homogeneous flow, so no temperature gradients, no mean velocity gradients, none of that stuff, all right? I'm going to assume infinitesimal disturbances. And what that did was it let us see just the basic properties of the Navier-Stokes equations, and it allowed us to see that the Navier-Stokes equations support the presence of these three canonical disturbance modes, which within those approximations are independent of each other, all right? And they're also sourceless and sinkless. There's no sources and sinks of those disturbances. Now I want to think about what happens if we start adding some reality, what happens. And the main thing that happens is that the modes start to couple and interact with each other, and also you start to get sources and sinks of these modes. So there's three ways in which these disturbances couple. They can couple through boundary conditions, they couple in regions of flow and homogeneity, and they couple through the action of non-linearities. Okay, so let's talk about those for a minute. Boundary conditions. a simple example would be, let's suppose I have this is supposed to be a straight wall. Let's suppose I have a sound wave that's a plane sound wave impinging on that wall, all right? So these would be lines of constant phase. How many of you have solved this problem before in acoustics? Nobody? Okay. Well, usually when people take sort of an Acoustics 1 class is to analyze this problem, we say, okay, no penetration boundary condition. So in other words, U dot in, so U dot in will equal 0 at the wall, okay? No penetration boundary condition. And it turns out that when you apply that boundary condition, the only way you can satisfy that boundary condition is if you have another wave which reflects at an equal and opposite angle, right? So this would be theta incident. This would be theta reflected. This would be the incident amplitude. This would be the reflected amplitude. And the only way you can satisfy that boundary condition is if theta I is equal to theta R and AR is equal to AI. Okay? So this is why sound waves reflect off of walls, because of boundary conditions. Now, okay, but there's also a second boundary condition, right? And that is U dot, I'll just call it T, where T would be my tangential vector, the no-slip boundary condition. That's also 0, right? So the velocity disturbance induced by these two disturbances, although one's going down when the other's going up, so if you add them, they give you no normal velocity. They're both in the same direction, so they would give you a tangential velocity. So how do we satisfy this no-slip boundary condition? Well, the only way you can do that is that if this acoustic disturbance also excites a vortical disturbance at the wall. Which kind of makes sense, right? You know, you're setting up a boundary layer. So you're also going to be generating a vortical disturbance, which helps you, which gives you a no-slip boundary condition. So this is an example of coupling of two disturbances. You started out with just an acoustic disturbance, but when it interacted with the wall, because the boundary condition doesn't care about separate contributions of acoustic and vortical. It just cares about what's the total velocity, right? The boundary condition is there's no normal velocity, no tangential velocity. And so you get coupling between disturbance modes at boundaries. So in this example, the acoustic disturbance excites a vortical disturbance because of the wall boundary condition. All right? And so another way this is another way of saying that the acoustic wave is damped because of the no-slip boundary condition, because what happens is that you have a certain amount of energy in the incident acoustic wave. Some of that energy is in the reflected wave, but also some of it is put into the vortical disturbance. So the reflected disturbance has a smaller amplitude than the incident disturbance because some of the energy in the incident wave went into the vortical disturbance. All right? And so this is a common observation. If you look at acoustic textbooks, you'll find formulas for sound wave dissipation at walls. Well, the energy isn't going poof into the ether. The energy is just getting transferred from one disturbance mode to another. So the wall provides a mechanism for the conversion of irrotational, compressible kinetic energy getting transferred into kinetic energy that is rotational and incompressible, the vortical disturbance. And so it shows up as acoustic. So it acts like acoustic damping, but overall energy is conserved. It's just that energy is redistributed between these two modes. So that's one way you get coupling. Another way you get coupling is in regions of flow inhomogeneity. All right? So wherever you have spatial gradients in mean properties, when a sound wave propagates through a region where the mean temperature is varying, or when a vortical disturbance propagates through a shear layer, you excite all the other modes. All right? So as I just mentioned, when you propagate a sound wave through a shear flow, you generate vorticity. When you take an entropy disturbance and you accelerate it. So if you have, flames are really, really prominent sources of entropy fluctuations. They generate a lot of entropy. And if you accelerate an entropy disturbance, that actually acts as a pretty powerful source of sound. This turns out to be a, are any of you working on combustion noise problems? No? Okay. Well, I'll just explain this a little bit real quick. So here's my flame. And as I just mentioned, flames make sound, right? So they make sound. These are sound waves propagating away. We call this direct combustion noise, right? It's a noise generated by flames. Well, it turns out that the flame is not only making sound, it's also making vortical disturbances. It's also making entropy disturbances. However, those vortical and entropy disturbances are just convected out of the system, right? If I have an open piece of pipe, the entropy disturbances, they're carried by the flow. They're just carried out of the system. Vortical disturbances are carried by the flow. They're carried out of the system. The acoustic waves, on the other hand, acoustic waves bounce or reflect very efficiently off of open ends of pipes. So the flame is making all three disturbance modes, but the acoustic energy remains trapped inside of the volume, whereas the other disturbance modes can leave it. However, the situation slightly changes if I accelerate the flow, like add a nozzle, right? And it turns out that if you take an entropy disturbance, just a convecting entropy disturbance, and you accelerate it, that acceleration generates sound. Okay? And so you will oftentimes, these are sound waves being generated. Sound will be generated in the nozzle by, in entropy disturbances just means that you have a fluctuation in temperature and density. It's an incompressible temperature density fluctuation. But what this means is you take a straight piece of pipe, that entropy disturbance just convects out of the system. You accelerate that disturbance, you're going to make sound. We call that indirect combustion noise. Versus this is direct combustion noise. So the one, it's combustion noise made directly by the flame. The other, it's indirectly made because the entropy disturbances get converted into acoustic energy by the nozzle. Yes?
The sound will be generated in the nozzle or at the exit of the nozzle?
Wherever there's acceleration. So wherever the flow velocity is being changed, you're going to be generating sound. And it actually turns out that there's a lot of discussion in the community out there that for example, jet engines are making sound. What's the dominant source of sound generation? Is it direct combustion noise or indirect combustion noise? Because if you're trying to minimize the noise, obviously these are different mechanisms, and then the cure, so to speak, for the problem would be different. So where this kind of problem, where people are worried about this is that for jet engines, oftentimes the dominant noise source is from jet noise, right? Propulsion generating jet engines. However, things like auxiliary power units, where you don't have these high velocity jets needed for generating propulsion, the combustor is oftentimes an important, what's called core noise, the noise from inside the engine, such as the combustor, is oftentimes an important source of noise. And then that leads to the question, which one is making the noise? Anyway, but it all comes back to the reason I'm introducing that. It's this coupling that happens in regions of inhomogeneity. Yes?
What is the mechanism for the conversion from entropy to acoustic mode?
Yeah, so what's the mechanism for generation of indirect combustion noise was the question. So if you go to the Euler equation, or just Newton's second law, force is mass times acceleration. Whenever you accelerate, it takes a force to accelerate something, right? So there's a pressure gradient across the nozzle. Excuse me. So suppose that the mass of the density of what I'm accelerating through the nozzle is not constant. It's changing. Well, if the density is lower, to do the same amount of acceleration, it takes less force than if the density is higher, for instance, right? Now imagine the density is oscillating. So the density is not constant. It's going to require a time-varying force to shove that through the nozzle, right? Well, what gives you a time-varying force? That basically means you have a time-varying pressure gradient. And as we've talked about, pressure fluctuations are essentially synonymous with acoustic disturbances. So the entropy disturbance is the density fluctuation, which is being accelerated, which excites an oscillatory pressure gradient, which gives you acoustic waves. Yes?
I think the nozzle increases the dissipation of energy of acoustic field. So is it correct to say that direct combustion noise is bigger than the indirect one?
So when you say the nozzle dissipates acoustic energy, what do you mean by that?
Yeah, is it correct?
Well, so the nozzle is a very efficient reflector of acoustic energy. So in other words, when sound waves from the flame hit the nozzle, a significant fraction of that energy comes back. It reflects. Some of it is transmitted through the nozzle, and that's what you hear. By the way, so the same thing goes to, I keep going back to this analogy of an organ pipe, and I've talked about how an open end of a pipe is a really efficient reflector of sound energy. So what you're hearing, when you hear an organ, only a small fraction of the sound, of the amplitude of sound fluctuations in that organ pipe is getting radiated out. You're hearing just a small fraction of the acoustic energy. Most of it is trapped and is just bouncing around inside of that organ pipe.
Direct combustion noise is the same thing as broadband dominant fluctuation.
So the direct combustion noise is induced by broadband velocity fluctuations cause oscillatory heat release, which give you direct combustion noise. It's not the same, but that's the mechanism for direct combustion noise. Yes?
Will these vortical and entropy disturbances get reflected from the gross boundary?
No. So vortical and entropy disturbances, by definition, can't be reflected because they're carried by the flow. And so the flow can't go through a boundary, right? But what happens is that when they impinge on boundaries, they can generate sound waves, which would then propagate back, and it would look like reflection. But remember, vortical and entropy disturbances are always they're always carried by the flow, so they're gonna follow the flow wherever it's going. Okay, so one last thing. So we've talked about two coupling processes. The last one is non-linearity. All right. So nonlinear interactions cause both create disturbances. They also cause coupling of disturbances. So I gave an example already before when I was talking about pressure fluctuations induced by vortices. Vortices make sound, but it's a nonlinear effect. And that's actually what I have here, jet noise. So to understand jet noise, you can't linearize. Okay, why don't we, it's 3:30. Does anyone have a question before we take a break? Yes?
The impinging oblique acoustic wave problem that you showed.
Yeah.
Aren't the two normal and tangential boundary conditions simultaneously satisfied if the wave reflects back along the same path?
Okay, so you're asking if my wave went like this and then came right back, would that satisfy the boundary conditions? Let's see. I have to think about that one for a minute. I don't think, because what you have to do is you have to satisfy the boundary condition at every spatial point at every time, and I don't think you'd be able to do that. I'd have to sit and work it out. But
basically, u dot n will be 0.
Yep, and u dot t would be 0. No, I get what you're saying, but I'm not sure that that boundary condition would satisfy the boundary condition at every spatial point simultaneously. I have to, like I said, I have to think about that for a minute. Good question. Yes?
Now your Bunsen flame is just, it's a free flame.
So the vortical, the shear layers, when you have that open jet, you have a shear layer, and that shear layer is hydrodynamically unstable, and it will oscillate even without acoustics. So it's impossible to always get rid of acoustics because sound waves will be reflecting. Even if that flame is an open flame, that duct upstream of it's not open. So you always have a little bit of sound waves bouncing around. So you can never totally divorce the problem from just acoustic reverberation in your flow section. Okay, why don't we take a break and we'll reconvene, talk about flame dynamics.